Last but not least, we have a mixture problem. Here's the key to the mixture problem. The concentration of the final mixture must be between the concentrations of the two solutions making up the mixture. Now that sounds like a bunch of hubbledy-bubbly, really. Think about this in terms of color. Okay, so I have a dark red over here, and I add white to that. So what happens to that red? If I'm adding red and white together, what do you get? Pink, right? The more red you have, the darker the pink. The more white you have, the lighter the pink. But regardless, it has the pink is between the red and the white. It's just a matter of which one's more concentrated, what do you have more of, determines the color of it. But the final mixture that I want to get is pink. So I'm adding red and white together to make that pink. And so that's what I'm talking about whenever I say between the two mixtures. We're going to have things like concentration. So if I have a 50% concentration of red and a, 10% concentration of white, and I want to obtain a 30% concentration of pink. So the 30% is always going to be in the middle of the two values that we have. And that makes sense, right? You have something that's strong, you add another thing to it, it weakens it. So you have this strong 50% red. When you add your white to it, it weakens it to give me my 30% pink. Okay, check this out. Again, remember, we're not touching anything, just read it first. Lisa Harmon is a chemist. She needs a 20% solution of alcohol. She has a 15% solution on hand as well as a 30% solution. How many liters of the 15% solution should she add to the 3 liters of the 30% solution to obtain her 20% solution? Holy cow. Woof. Now, here's another situation to where a table comes in handy. Let's make one. When you make your table, you have 3 columns here. You have your strength, which is your percentage. Then you have the amount that you're looking at, your liters in this case, pardon me, whatever it is that you have. And then, lastly, it's your amount of pure. So, you have your 2 values. So, you have your 2 amounts that you have, you have your 2 amounts that you currently have, and then the 1 amount that you're looking for. So whenever I make my chart, I like to put the double line at the bottom because that tells me it equals. So let's fill it in. She needs a 20% solution of alcohol. So if I need a 20% solution, that's what I'm going for, and that's the amount that I want. She has a 15% solution on hand as well as a 30% solution. So you know that we have 30% solution and a 15% solution. So notice what's equal to the 20% is between the 15 and the 30. And that's what we want. That's what we're talking about. You have a heavy concentration of the 30, a weak concentration of the 15. You put those 2 things together to give you your 20. Okay. Now, what else do we know here? We also know that she has 3 liters of a 30% solution. It says how many liters of the 15 should she add to the 3 that's in the 30? So the amount that we have right now is 3 for the 30% solution, and we don't know how many for the 15. That's going to be our variable. So anytime you introduce a variable, you have to write your let statement. So let x equal the amount of the 15% solution. Cool. Now, let's check and make sure we've got this. Lisa Harmon is a chemist. She needs a 20%. She has a 15 and a 30 on hand. We've got that in a percent column. How many liters of the 15%? We have that right there with the X. And we know she has 3 liters of the 30%. Okay, let's do this thing. Notice in my chart, we have a whole bunch of blank spaces. This is where we get to fill those in. The reason why I put the double line is because we are combining these two mixtures. We're combining the 30% plus the 15% in order to get my 20%. So we're going to add those two mixtures together because we want to determine how much we're dumping in. So the amount of 20% that we have is X plus 3. The amount of pure, now this tells me what percentage of pure I have. Because this is a 30% solution, you can change that to a decimal. So 30%, when you move the decimal twice, is the same thing as 0.3. So I have 0.3 times the 3 liters that we have. Same thing with the 15%, you want to change it to a decimal again. So you have the 0.15, and then that is times X. The same concept applies. You add those up to get your 20% here. 0.2, because I'm moving 2 places, to get the X plus 3. So 20% of however much I put together is going to be how much I have of the 20% solution. Good. Now as soon as you know your amount of pure for everything, that is your equation. You have 0.3 times 3 plus 0.15x equals 0.2 times your x plus 3. And there's your equation. So you do the chart so that you can set up your equation and you go with it. Now I know some ideas out there say, okay, multiply through to get rid of the decimals. You have a calculator. There's a reason why you have a calculator. Use it. There is nothing wrong with that. So let's do it right now. If we have 0.3 times 3, that's going to give me a 0.9 plus a 0.15x. Distribute this 2/10 to give you a 0.2x. Oh my. Plus a 0.6. Now combine. Again, I want to keep my lead coefficient positive, so I'm going to subtract a 0.15x. And at the same time, I'm going to subtract a 0.6. That goes, that goes. So now I'm left with a 0.05x is equal to a 0.3. Divide both sides by a 0.05. And x equals 6. Cool. So x equals 6, well, big deal. What does that actually mean? You know, if x is 6, we have this handy thing called a let statement. So, what do we do to finish this off? Therefore, Lisa needs, that's an E, 6 liters of the 15% solution. And that's it. Cool.